Now, when we're talking about electric matters, generally electrostatics are kind of nice and interesting and they lead to a number of strange things, but most of the time we're talking about electric current and electric circuits. Now, when we talk about electric circuits, what we need to define is what we call electric current. Electric current, I know, really makes a lot of sense, but the symbol that we use for that is I. And I is the amount of electric current going through there. When we look at the average, we figure out how much charge is going through a wire in a given amount of time, and delta T is that amount of time. And so what we do is we look at that as we look at the instantaneous value of that current, and the units of that are what we call amperes, which are coulombs per second. So it's an amount of charge going through a wire in a given time. So we can solve some problems involving current just with the definition of current, which is the amount of charge passing through a wire in a given amount of time. But in terms of the units that we use amperes. To describe exactly what's going on in a wire, we also need to define what we call voltage. Now, that's not the technical term. That's the term that gets used a lot, but it's actually what we call is the electric potential difference. So electric potential is similar to potential energy, but not exactly the same. We call that voltage. It's a difference between the electric potential between 2 points on a wire or in a circuit. But the measure of that is called the volt. That's why I don't like to call it voltage, because it's really annoying to have voltage measured in volts. The actual term is electric potential difference, and it's measured in volts. So like a 9-volt battery provides a 9-volt potential difference, electric potential difference. And we call that the voltage. It makes sense, but you can get tangled up in the words if you're using voltage for everything. But it's named for Alessandro Volta. He made what's called the voltaic pile. It's the first electric battery, and most like AA, AAA type batteries are this type of battery. So if any of you has taken apart a battery, you'll see it's usually there are different types, but a lot of them are either stacks of smaller batteries, or you have things that are wound up paper inside of each other that are basically layer upon layer upon layer, but it's just in a different configuration. And so just a simple voltaic pile, each element, the simplest old ones were zinc and copper that would be excuse me, separated by an electrolyte cell. Each one would provide a small amount of electric potential difference, a small voltage. And then to get the total for your battery, you would add up all those individual pieces. So if each one was 5 volts, in this case, you can see there are 1, 2, 3, 4, 5, 6, and if each one was 5 volts, this would be a 30-volt battery. But in each case, you add up the individual elements to get the total. And to actually get electric current to flow, what you need is a full circuit. So you need a path for the electric current to follow from your source of energy, so in most cases a battery, all the way through whatever it is that's using up that energy, so in this case a motor. So you need something that has a full circuit, a full path for that to go through. If the wire is unplugged or is broken, all of a sudden the motor would turn off, not because it doesn't have access to the positive terminal, but it's because the charges don't have access to both terminals. They can't travel in that full loop, and so it just stops. So to describe what's going on inside one of these materials, we need something called Ohm's law. What George Ohm found was that if you take a battery and you use different materials to have current flowing through them, it takes some amount of energy. They don't naturally just let current travel through them. And so he realized that the more energy each charge is given, the electric potential difference or voltage, you get more current. And then he realized that if you had a type of material that had a greater resistance, you would get less current. And so what he came up with is his version of what we call Ohm's law, is that the resistance is equal to the ratio of the amount of voltage required divided by the amount of current you get out. And that's called Ohm's law. I usually write it, most people usually write it in this way, is that the voltage, or electric potential difference, equals the product of current times resistance. And so that gives us the units of resistance are volts per amp, and we call those ohms. And the symbol for that is the Greek letter omega. So it's named after George Ohm. And the symbol is the Greek letter omega because ohm and omega kind of sound similar. So we get that. And when things follow Ohm's law, what you get is a nice graph that looks like this. Because V equals IR, you kind of see a nice linear shape. And so in this case, the slope of that line will just equal your resistance. But if things don't follow Ohm's law, if things are a little bit more complicated in how voltage and current are related, you get something like this, so like an LED or just a plain diode. You don't get anything until you get a certain amount of voltage, and then you start getting more and more and more current. The more and more voltage is used up there. So a diode doesn't follow Ohm's law, and the really fancy way we refer to that is a non-ohmic device.